everyone. Welcome to the algorithm seminar. Today, we're happy to have Vitaly here to give a talk. He's currently an assistant professor at City University of London. His research focuses on self-adjusting systems and practice and theory of parallel and concurrent data structures. Before joining City University of London, Vitaly was an assistant professor at ITMO University for a while, and prior to that, he was a postdoc in IST, Austria, under the guidance of Professor Dan Alister. He received his PhD from Paris 7 Diderot and ITMO University under the guidance of Professor Petr Kuznetsov.
Jimmy, thank you very much. What do you see right now on the screen? Like, do you see some green things that?
Yes.
Okay, great. I just never worked with that prior, so I have no idea how it works. So today I will have a talk about concurrent data structures that appear to be also self-adjusting and how to do with that. If you will have any questions throughout the talk, please just interrupt me and ask the question. I would be happy to do that because it's better to understand something rather just omit it, because some parts can be a little bit complicated. So we are going to work with index data structures. And first, our index data structures usually have three operations. This contains, insert, and remove. So like for indices in databases or something like that, I understand like there should be a little bit more queries that can be performed, but we consider only the three simplest one. And there exists a lot of range queries that can be run on index data structures. But the main things for key value storage is contains, insert, and remove. So there are lots of different index data structures in the world. The most widely known for everyone are binary search trees, while usually in databases they use B-trees, right? Like maybe I'm incorrect, but as far as I remember, that's what the state of the art is. But the issue is that most of these data structures perform operations with the same complexity. So no matter what elements does it request or anything else, the complexity is still logarithmic in the number of elements. But there exist trees that adjust to the load. So what does it mean is that usually this means that the more frequent you request an element, for example, for contains operations to get their value, or to change the value, you will do this faster on the more frequently request elements. Their most well-known self-adjusting tree is SplayTree. I hope that most of you understand what it is. I will briefly talk about this a little bit later. So there is Tanga trees, and etc. So let us, for a moment, think about notions of optimality. So usually, you consider that the complexity of all operations is the same. But there is an optimality named static optimality, is that you're given the request that your tree performs, and you want it to be as the best static tree that you can build given the request in advance. So this is static optimality. This means that our tree performs in the same complexity as the best static tree possible. Dynamic optimality is a little bit more elaborate, and it means that there is a dynamic tree given the request in advance. So like dynamic here means that in between the requests, you can do some changes to the data structure. So dynamic optimality is much harder to get. Well, static optimality is relatively easy as its own. There are other notions of optimality like static finger, working set, and etc. But in this talk, we will be care about static optimality. So you can see on the bottom of this is the screenshot from the Tarian's paper on SplayTree, and the idea is that qi is the number of requests to an element I. So this means that their total amount of the total complexity is the sum by each element, where each operation costs the total number of logarithm of the total number of requests divided by the number of requests to an element I. This is kind of from their information theory, this kind of expected result that the best you can do for an element is logarithm the number of requests divided by the number of requests per an element. The most known static optimal binary search tree is SplayTree. Some of you know maybe that it's conjectured to be dynamic optimal, but nobody could prove it. And the idea is that there are different rotations. So there is, as far as I remember, or it's written here, it's zig, this one is zigzag, and this one is zigzag. And the main idea is that suppose we are looking at the element X, we are looking for, we take an element X and put it into the root of the new tree. So this means that each time a node is requested, to be more precise, a key, it will be rotated to the root. By that means that, kind of, if you think about it, if your element is requested more often, then it will be closer to the root always. And so we will answer the queries for it faster. But the question, what do you think? Is it good for concurrency? Is this data structure good? Is it data structure is very easy to do concurrent? What do you think? Concurrent, sorry, maybe I presumed something incorrect. So the concurrent means that there are a lot of processors working on these data structures and trying to apply operations on it. So we're working in the concurrent system. Is it clear?
Yeah, no, it would be hard to do it concurrently because everyone would be fighting for the top of the tree.
Yes, exactly. This is exactly the right answer. Yeah, everybody will be trying to put himself in the root, so there will be a problem. So the only existing concurrent self-adjusting index that is for a long time was available is CBTree, up to the moment when we came out with concurrent data, other concurrent data structure. So let us look a little bit on the CBTree. So it is based on concurrent AVL tree by Bronson. The main idea of this tree is that when you go down the tree, you kind of maintain hand-over-hand validation. So why do you need this? So suppose that you have an AVL tree. AVL tree has some rotations, and you have concurrent rotations. And you go from the root to somewhere, and you go, and someone rotates a tree, and you can get to the wrong branch because you decided to go there. So there should be some specific things to be done. It is done usually with hand-over-hand validation. So we kind of take a node, we take a next node, and check that nothing has changed in between them, so nobody of them rotated, and we can go down. And in AVL, as you know, the main idea of AVL is that the heights of both trees, both the children trees, are different by 1, right? That's how it leads to logarithm n. So the idea of CBTree is that the number of requests per the child divided by the number of requests for the whole tree with the parent is not less than some constant. Here it's alpha. And if it is not, we just rotate it. This is kind of the high-level explanation of what's happening there. It's a little bit more elaborate, but we will stick to this one. But of course, there is a problem that when you do hand-over-hand validation to do this, you still have some problems with concurrency there. And do we have in SkipList such problems? And apparently we do not have. So the main idea, the main difference between SkipList and the tree is that you can never get to the wrong branch, because in the SkipList you will always find a next node. So let's look a little bit, like, let me remind you of what SkipList is. So in the SkipList, we have the set of elements, and each element has a tower of random height. So it is of height 1 with probability 1/2, then it's height 2 with the probability 1/4, and so on and so forth. So if you have n elements in your tree with high probability, your height of the maximal element is logarithmic n. And then for each level, we have a linked list. So like this is level here. And then, for example, we want to request an element 7. You go from the top list, then we look on the next node. You see that it's incorrect. So we go down by the skip list. Then we go to the right. We find 4. 4 is less than 7. Then we go to 6. We found that 6 here. Then we look on the next element. It's like kind of infinity. So 7 should be somewhere in the down. So you go down. You consider that the next node is 9. So 7 should be again down. So we go down and we found 7. Okay, great. And it is proven that given this random thing, your expected search time is logarithmic n. I hope everyone knows that. There is a self-adjusting skip list existing, but it is very hard to make concurrent because it asks too much synchronization due to the problem that it's split into several data structures, separate data structures, which are very hard to synchronize properly. This is also almost the case for most self-adjusting data, static optimal and dynamic optimal data structures that they work in several parts. So we'll explain right now how to, from skip list, make Splay-List. The idea is that with an element, a tower contains the number of requests to this element. And the main idea is that we kind of try to optimize the path to the towers that have more requests in them. So you can see here on the picture, the idea is that we will go from left to the right, as usual in the skip list, and then on the path back, we will update the heights of the nodes. How we will do that? We will have two conditions. So for the descent condition, we consider for each node the number of elements in its subtree, kind of. So this is kind of subtree. So we have V, the next element is U, and all the nodes between V and U on the lowest level are in its subtree, and the same with U. And their idea is that if there are not many elements in these two subtrees, then one of the nodes should be smaller. That's a reasonable thing to ask. So if the number of requests not very much, we decrease the height of the node. For the ascent condition, it's a little bit complicated. So we look on the suffix, on all the elements on the suffix, and if there are enough requests to all the elements in the suffix, we increase the height of U. Let us look on the simple example. So here is an example. We have on the bottom we have the number of requests per an element. So here is this one is 1, 1, and the 6 was asked like 6 times or 5 times already. Each element further to the top calculates the number of requests to the subtree without their elements in the subtree. So for example, this one considers this one. 0 considers that there is nothing on here, so it is 0. 2 is considered as these 2 guys, and here is again 0 because there are no elements in here. And for example, here is 5 because there are like number of hits here is 5. And we make an update. So here is an operation that kind of insert or change their value of the key 5. So we go to the key 5, and then we go on the way back. So let us look what's happening there. We look on 1, 2. Nothing can be changed here. Nobody is going down. So we look on these guys. So the first one looks on the right of it, and it finds, okay, I have 3 requests here. And if we look at the condition, we compare this 3 with 11 divided by 4. I'm not sure that you need to be aware, so we just compare it with some value for this height. And we found that we have to go with 4 on a little bit higher. Then we continue following the path back, and we find right now this node has 0 and this node has 0. This is very small amount, so we need to decrease one of them. We decrease this one, and here it is. We updated our Splay-List. So the idea of all the operations are pretty simple. So for the contents, you traverse forward, traverse back, increase all the hits counters, and apply all the conditions. Insert is a little bit more elaborate rather than in SkipList. We go to the lowest level where we have to insert an element. We insert a node with the number of requests 1, traverse back, increase all the hits, and apply all the condition. The deletion is very important here, is that deletion doesn't delete an element physically. It deletes it only logically. So it just marks an element as deleted, traverses back, and apply all the conditions. To get rid of a lot of physical nodes, we claim that if the number of hits per logically deleted nodes is very high, then we rebuild the whole data structure from scratch. I think this is quite expected, and this is pretty simple in the terms of amortized time, because if you make m requests and half of them are for the deleted nodes already, then we can rebuild all the data structure in O of m, and we can amortize against these delete operations. The analysis is pretty simple. We just prove that on the path to any node, there can be only some constant number of elements on the same height. We prove that it's no bigger than 8. And thus, we can prove that the total operation cost is d plus the required logarithm of the number of requests divided the number of requests per u. Why so? Is that when we go down, we kind of split the number of requests per subtree by 2 times. So that is why our target node will have the height of logarithm m divided by the number of accesses to the sound. And we can prove that we can amortize the descents that are going to be done on the way back, and prove that the operation is indeed what we require for the amortized time. So this means that our data structure is static optimal in a meritized sense. Okay. There is still problem, right? So suppose we're going to do concurrent updates to the data structure. What do you think? What is the problem? Still, like if we will make exactly as it is done right now. So we just take locks on the path there and then to the path back.
Yeah, those paths will lock a lot of your towers, right?
Yes.
You know,
Yeah.
the locking pretty much a large part of the data structure.
Yes, indeed. But mostly, like what we really right now care is the similarity between CBTree and this one, or SplayTree and this one, is that you will have locks on this, like the largest nodes, and everybody will be serialized over that. So we need to make some updates there. So the first update that comes to mind, to be honest, like that is a little bit not from the concurrent side, but in general side, is that we can do rebalancing periodically. So only 1/c operations will make this update back. All others are just going down and update the counters. That's it. So we proved for Splay-List is that if we perform rebalancing with the probability 1/c, the C will appear in the complexity and that's it. So it will not fail the complexity at all. And if C is constant, then you will have the perfect complexity there. And this implies stronger guarantees because CBTree was never been proven to have this periodical rebalancing. Okay, so let us go about the concurrent implementations. I will give you a brief intuition how to do this. So at first, our current approach just locks all the elements on the path to do forward path and backward path. It appears that we don't need the backward path at all. And only the first element on the level can ascend. So if we look on this, oh, sorry. If we look here, so suppose these are the guys, this is the first guy, this is second, this is third, this is fourth. It appears if to look on the ascent condition, probably only the first guy can ascend. So we can understand whether it can ascend by going in the forward direction. So we go in the forward direction, check if it can ascend and go forward. Also, we do descents on the path forward. So if this guy has to be descended, we descend them on the forward path. And for that, you will just need hand-over-hand locking. So you take a node, take the next node, check the conditions, release it, release the first one, take the second one. This is the first problem. And as you can see, there is still the problem is Al said, is that everybody will kind of have problems with the root still. But since we apply relaxed operations, there are no many threads will be conquer for their main node for the head and so on. There are some other things. The main thing is that how to implement the deletion. For deletion, we usually do logical deletion, but when we check the number of elements, we just take a big lock and rebuild the whole data structure. Okay, so let us look briefly on the experimental evaluation that we have here. We have 4-socket machine with 18 threads. And we have the following interesting workloads. So usually concurrent data structure or indices, concurrent indices are are tested on their uniform workload. So it considers like YCSB, TPCC, and so on. Sometimes there are zip distributions, but not always. So we decided to come out to show that our data structure indeed adjusts to the workload. We just take a more skewed experiments. This one for example, this one means like that the number of elements is 10 to the power of 5, and we have 90% of requests. 90% of requests is on 10% of elements, and just it. And the other 10% of requests is for 90% of elements. So here is like 10% of elements gets a lot of requests. And for example, here is even more skewed. So it has 1% of elements gets 99% of requests. So we looked on the sequential execution of the data structure. So we compare against SkipList and CBTree, because it's the self-adjusting data structure, and SkipList as the one because we based on it. And we find out that on our skewed workloads, Splay-List is faster than SkipList, but it is not that faster than CBTree, unfortunately. So as you can see, for the most skewed workload, CBTree is faster in 2.36, while our Splay-List is faster than 2.01. So that would expect it because SkipLists are much slower in terms of everything than the binary tree. But as you can see that we indeed get more skewed, so their average path becomes shorter and shorter. So it was 1.3, then it's 1.38, then 1.76. So it is indeed works. Then we looked briefly on their operations. So here is the blue one is our data structure. The green and red are CBTree, and the orange one is SkipList. It is not like, mostly we want to look on the update rate 100. On the left and on the right, you can see with different update rates. So the update 100 means that only 100 of operations are doing rebalancing phase. So, and if we go further with more skewed workloads, as you can see, our data structure becomes closer and closer. And on 95.5, it outperforms SkipList. On the most skewed, it outperforms like on 1.5 approximately. For ZipFan, it outperforms, but not that much, somewhere like by 20%. So this is the final result. Here on the left, you see the results of the SkipList in comparison to the, sorry, it's a little bit incorrect. Here should be Splay-List, sorry. So this is for Splay-List, and this is for CBTree in comparison to SkipList itself. And here, as you can see, we work on skewed workloads better than CBTree. So this is my part about SkipList and Splay-List. I hope the next part will be a little bit more exciting. But the main thing that can be very interesting here is that we provide a very simple SkipList with adjustment to be static optimal. Then we prove the guarantees for the relaxed version of this data structure. And we implemented the concurrent implementation that works quite well on very skewed workloads. I understand maybe it's not that exciting because the workloads are very skewed, but it still proves the point that there is a possibility for concurrent self-adjusting data structures. So do you have any questions currently for this part? Okay, so if there are no questions, let me go further. I hope you will like the next a little bit more, because here is a little bit more specific. There is some skip lists, some things. The next part is mostly will be about their sequential self-adjacent data structures that have a potential to become efficiently concurrent one. So we will be talking about multi-way static optimal trees. So there exist a lot of different multi-way trees. By multi-way, I mean not binary trees where they have only 2 children per node, but several. And the most prominent ones that are used, like kind of the B-tree is, I mean, I hope everybody knows what B-tree is that each node has either B+1 or 2B children. And interpolation search tree. And what is their best thing about interpolation search tree is that it can answer the request in double logarithmic time if we have smooth distributions. That may be kind of interest for you. So this is pretty nice data structure. It's maybe you heard about machine learning indices, current machine learning indices. As far as I remember, Tim Kraska was at Google at that when he came up with learned indices. This is kind of learned index, but very simple, and it gives the proper guarantees. Okay, there exist different static optimal B-trees on the market, but usually they do not support efficient range queries. Because, as I said, the static optimal data structures are usually split into their parts. And since they're split into the parts, the range queries should be done in each of these parts, which will give you a higher complexity, like logarithmic squared complexity or something like that. And obviously, this is challenging to make concurrent. Also, we are not aware of static optimal interpolation search tree up to right now, and it will be not static optimal, it will be even better. So let me talk briefly about what interpolation search tree is. The idea is that we have n elements in all tree. The root node, this is kind of the ideal tree. The root node contains square root of n elements, and it divides on square root, approximately square root of n children, and so on. On the next level, it's square root, the fourth root of n, and logically down, and that is why the height of this tree is log n. Not obviously, like, if you want to search for an element, if you know in which shell to go, then it's obviously double logarithmic time, right? So the only problem is to find the proper child where to go. And for that, we'll have the request that will ask this index, and this index will find the corresponding representative in their node. And then, like, for example, representative 1 has as the left part the child C1 and the right part C2. So what is the idea? So we create an array ID of size n in the power of alpha, where alpha is between 1/2 and 1. And as the way, it's pretty simple. It takes the whole range, and for each I, it takes an element from this range. Like, it kind of splits this range into m equal elements. And for each of this element, we find the representative. So to find a representative for our element x, we just find in which segment of length m in which segment where we split on M parts, where it lies, and then we search to the left or to the right, depending on whether we got to the proper representative. We can use linear, we can use binary jumps. If you use binary jumps, then you can get, in the worst case, logarithm n time to find a position in the node. And it appears that if everything is smooth, like there is a pretty complicated definition from the paper which is smooth, but for example, all our distributions that we talked previously about, like Zipfen or uniform or distributions, they are smooth distribution as appears. And the fact is that if it is a smooth distribution, then this identifier will point us almost to the right representative. That the right one will be really close, and it will have like off one time in expectation for the search in the node. Unfortunately, this works only for integers or doubles, but this is pretty interesting thing. I understand that B-tree is a little bit more generic, but the idea is that for most existing distributions, we can get search in the constant time. That's pretty exciting. How the operations work, so we have a traversal stage. We go from the root to an element, you find the proper subtree, and then we go down, and when we want to insert, we insert an element as a leaf, and we have a remove operation that just marks for deletion. Obviously, there is a question how to rebalance everything, and to rebalance, we just do lazy rebalancing. Is that if there are too many updates in the subtree from the last rebuild, we rebuild the whole subtree from scratch to the ideal one in linear time. So we can amortize the updates, the rebuild to the updates that were in this subtree. So in the total, we will get log n as expected depth. And as the worst case, we'll get logarithmic squared time worst, because in the worst case, the height of the tree can be logarithmic if we because we rebalance amortizingly, and logarithm n is to find the proper node, proper child in the node. So logarithm squared is in the bad case for non-smooth distribution, just for any distribution. And it appears that it can be done concurrent very efficiently, as their experience shows. And their idea is that their operations itself, insertions, deletions, are pretty easy to do concurrent, because either you insert a new leaf, which is just locking, or like pretty simple thing in the bottom of the tree, and the removal is just to mark thing. So the only problem here is the rebuilding. The rebuilding is the problem. So the processors, when he came to the subtree that is rebuilding, it cannot wait, because this will take a very long time. So it kind of goes and help another thread. So like if there are lots of threads come to the subtree, they work together, and it's pretty simple. It just goes to it just tries to build only some new subtree that is just chosen only for him, just only for this thread. It's a little bit elaborate, but it was implemented and everything was simple. So we know how to make lazy updates concurrently. This can give us an intuition on how to make concurrent self-adjusting multi-way trees. For that, because insertions will be the same, everything will be the same. We just need to come up with the algorithm that makes static optimal ideal trees, and that is it. After that, our data, like if we put this rebuild just in the same framework as IST does, concurrent IST does, we will get the simple self-adjusting, to be more precise, static optimal tree. And then we apply it for B-tree and interpolation search tree. So the idea appears to be pretty simple. For multi-way node, we just make sure, so we have all the elements, and to build the ideal tree, we'll take not each square root of an element, as in the ideal tree for the normal case, but we split the list of elements such that the number of requests per each sub interval is no more than square root of m, where m is the total number of requests. So it's not square root of m, like, because it's a little bit generic. It's d of m as the node degree, so it's like m divided by d of m. So we just want to split evenly not the amount of elements, but the number of requests. So for the binary tree construction is pretty simple. So we get all the elements with the number of accesses, then we split into 2B parts of approximately equal number of requests and go recursively. It's pretty easy to see that the depth of X is expected to be logarithm B of M divided the number of requests to an element, because each time when we go lower to the child, the number of requests per the whole subtree decreases by B. So we divide M by B several times to get the number of requests per element X. For interpolation search tree, there is nothing more complicated. I will just show you the complexities and parameterization. So for IST, the parameterization is d of m is square root of m. The B-tree is the number of subtrees is 2b. The ideal construction, the construction of an ideal tree maybe have not very good time. I mean, it has a very good time. So it's like depending on the number of requests, which is quite fine by us because we can amortize it. The construction of the whole subtree. The memory is not very good. So for B-tree, the memory is linear, while in interpolation search tree, our memory will be bigger because we have this ID array, which can be quite large depending on what we choose. So here we chose m in the power of alpha. And search and remove times, because remove is logical, we'll have that the worst time is logarithm m, and their expected time is for B-tree is static optimal, is logarithm m divided by the number of accesses. For interpolation search tree for smooth distributions, it is very interesting. So it's logarithm, and inside there is not m divided by the number of requests, but logarithm m divided by logarithm number of requests. So it's even better. And insert time is logarithmic m. The best thing of our algorithm is that it obviously allows for efficient range queries. And we even claim that this interpolation search tree works even kind of with removed elements. What do I mean by that? Usually, there are self-adjusting trees like SkipTree, SplayTree, and etc. They do not perform well under deletions, as they only provide the proof for contain separations or replace separations. Here we claim that their expected time here m is the number of requests to non-deleted elements there. So this means that at each point of time when you perform a request, it like logarithm m, the current number of requests to all the nodes to the tree, and not through the whole time, which is much better and interesting theoretical. We did some experiments, some sequential experiments. We had B-tree against our self-adjusting B-tree. We have interpolation search tree against self-adjusting interpolation tree. We have SplayTree as our main not competitor, but the main baseline. SA2T is if we consider not B-tree but binary tree, so it's because of that it's 2 here, and there is an additional data structure salt, which we just played a little bit and choose L. This means that the number of children of the node is not B or square root of M, but logarithmic M. This is just to play a little bit, because this doesn't change our algorithm at all. And here in the request, as you can see, the blue ones means that our self-adjusting B-tree outperforms the B-tree, the corresponding B-tree. And sometimes our self-adjusting interpolation search tree outperforms also B-tree here. And sometimes, for example, here it's 2.16, which is bigger than everything here. Then we added writes, additional writes, and as you can see, interpolation search tree is sometimes better than everything, our self-adjusting. The B-tree is also sometimes better. The blue ones means that we outperform their corresponding B-tree and interpolation search tree. Okay, so let me conclude. We presented a novel concurrent self-adjusting data structure based on SkipList with relaxed balancing. We presented on how to make multi-way trees self-adjusting in a pretty simple manner that allow also range queries, like efficient range queries. And we claim that these multi-way data structures can be made concurrent efficiently. So that's it from my talk. Thank you very much for your attention.